Good morning, everybody, and welcome to Analog Electronic Circuits. This is lecture 18. In the last class, we were looking at current mirrors, and this is the basic mirror. The output current. And what are the problems with this? Yeah, basically, output resistance is poor, and accuracy is poor. Therefore, accuracy meaning the ratio of I out to I ref. Okay, but what is the good point? Yeah, the minimum voltage needed is minimum voltage is just delta V, where delta V, let me remind you, is again VGS minus V. Right? So to fix this problem, what did we do? We said, well, the root cause is that this is a bad current source. We want to make it a better current source. So what do? How do you make a bad current source a better current source? You make that the input to a current controlled current source. And the simplest single transistor current controlled current source that you can think of is the common gate amplifier. And so that led us to the cascoded current source. And we discussed how this came about yesterday. This is I out. And what are the good things about this? So the output resistance is larger by a factor of GMRO, and therefore also it also turns out that, as we saw yesterday, the accuracy is also very good. Why? We discussed this yesterday. Why does this have very good accuracy? Yes, Chaudhary.
Means for M3 also the gate voltage will be delta V. So the gate voltage will be twice of delta V plus twice of V.
So the same current, we need a similar bias will be good. So for M3 the biasing should.
No, hold on. The gate of M3, right? At this point, I mean, in this picture, what is the potential of the gate of M3? 2 Vt plus 2 delta V, right? Is that necessary to keep M2 in the saturation region?
Yes.
If you want to get high output impedance, M3 and M2 must be in M3 and M2 must be in what region of operation? How did we come up with the gate bias of M3? The gate bias of M3 is what? What is the bias voltage? What is the voltage at the gate of M3? What is the meaning of it should be at the edge of overdrive voltage? The sentence doesn't even make any sense. What is it? No, I don't understand. What are you writing, man? I don't understand. Yes, Abhishek Chaudhary.
VG should be 2 delta V plus
How do you get that?
VGS minus VT is delta V. So
Why?
support the same current.
Yeah. So M3 and M2 have the same size. They're carrying the same current. So the gate source voltage of M3 will be VT plus delta V. So what must be the gate voltage of VG, or gate voltage of M3 must be? It is VT plus 2 delta V. Right? Okay. So what is so therefore the minimum gate voltage needed to keep M2 in saturation is, I'm asking you the same question and I still see blank faces. What is the minimum potential needed at the gate of M3 to keep M2 in saturation? It is VT plus 2 delta V. Okay, so why don't I just put therefore if I put VT plus 2 delta V here, okay, what comment can you make about the output resistance? Assuming M3 is in saturation. Remain same as remain what?
GM R naught times the previous R naught.
Yeah. So if I connect the gate to VT plus 2 delta V, right, that is enough to keep both M3 and M2 in saturation. And the output resistance will be
R naught equals GM R naught.
GM R naught times R naught, which is GM R naught square. All right. Okay. But then why did we connect it to VT plus 2 delta V? Why did we connect it? The gate, of course, is only if the VGS and the VDS are identical, right? Okay. So the gates, of course, are identical because they're shorted together. It's VT plus delta V, whereas the drain potential of M2 is delta V. So what comment can you make about the approximately what comment can you make about I out? I know it is less than IREF, right? But how much less is it? Can we estimate it? So in other words, if this voltage VG is tied to VT plus 2 delta V, what comment can you make about the current I out? Yes, Pawan Kumar. It will be smaller, but smaller by how much? How did you get that? So the difference in drain currents is basically difference in drain voltage divided by R naught. So what is so difficult about that? We did this in the last class. All right. So the the whole discussion started because this gentleman here said that the accuracy is good if the output resistance is high, but they are two fundamentally different things, right? Okay. In this case, if we tied this gate to VT plus 2 delta V, right? What comment can we make about the output resistance? It is GMR naught times R naught, which is an order of magnitude better than the basic current mirror. Is this clear to everybody? All right. However, what comment can you make about accuracy? What is I out? IRF minus capital VT by, is it R naught or GMR naught square? Why?
The current in the M2 will be less than means VT by R naught times.
Yeah. So basically, the accuracy is governed by the ratio of current between in the transistors M1 and M2, right? And their VDS difference is VT, and therefore it is VT by R. All right. Okay. So what comment can you make about accuracy here now? Is good or bad? Bad. So basically, all right. So accuracy has got nothing to do with output. Right. I mean, you can, as you can see in this mirror, I mean, it's another matter where how we generate VT plus 2 delta V. But what do you call? What comment can we make about the minimum voltage though? What is the minimum voltage needed to keep, to make this behave like a current source? How do you get 2 delta V? The drain potential can go one threshold below the gate, and the gate of M3 is at VT plus 2 delta V. So the minimum drain potential is 2 delta. Right. So the minimum voltage is not. I mean, it is of course better than, but you had to expect that in order to get this high output resistance, you had to expect to pay something, and what you're paying is a loss of headroom, and that is only by delta V, and that makes sense because if you stack two transistors one above the other, but remember that the minimum drain source voltage needed to keep a transistor in saturation is the minimum potential needed to keep a transistor in saturation. The minimum drain source potential is what? If you have a transistor, that's all I'm asking. Like we've done here, what is the minimum voltage needed to keep the stack of both transistors in saturation? It is 2 delta, right? So you cannot do better than 2 delta. Is this clear? Okay. Now, what do you call? So but if you want to fix the accuracy problem, what did we do yesterday? We recognized that the root cause was what is the root cause? What is the root cause for poor accuracy? Okay, so what should the gate be tied to? Gate of M3. How will we fix the problem? If we want to fix the accuracy problem, what will we do? Go step by step. What should we do? What is the root cause of the problem? The drain of M2 is basically delta V, but it should be delta V plus VT. So what should the gate of M3 be tied to? What should be the potential at the gate of M3. Yes, you in the last bench. Yeah. If the source of M3 is at Vt plus delta V, what should the gate be at? It should be 2 Vt plus 2 delta. Correct? Now, so the minimum voltage is delta V in this case, 2 delta V in this case. Alright. So now what comment can you make about accuracy? Huh? Yeah. So basically I out is simply, no, do you, all of you see why this, just putting an M4 there and forcing current into its drain doesn't result in a magically a gate voltage? Yes? No?
Yes.
Okay. All right. So that doesn't work. Okay. So what voltage do we need here? We need Vt plus 2 delta. Okay. The question is how do we get Vt plus 2 delta? All right. If I want to get Vt plus delta V, what will you do? I mean, if you want to generate a voltage which is Vt plus delta V, what will you do? You will take Iref and connect it into a diode connected transistor. Right. So this is giving me Vt plus delta V. Okay. Now if I want Vt plus 2 delta V, what do you think I should? Okay, let me lead you to the answer. What is this saying? This is if you write the equations, basically it's saying Iref is nothing but 1/2 un C of W by L times delta V the whole square. Okay, all right. If you now if we want to generate delta V by 2, Vt plus delta V by 2, what do you think we should do? Yeah, you can either do Iref by 4 or you push Iref by 4 is definitely something you can do. Alternatively, you can basically say you choose a transistor which is 1/4 the size, correct? And then the overdrive needed to basically support. If you reduce the size of the device by a factor of 4, but still pump in the same current into the diode connected device, what will the gate voltage be? This is W by L. Okay, this is W by L times 1/4. What is this gate potential? This is Vt plus 2 delta. Does it make sense? Okay. So now can you tell me how to generate Vt plus 2 delta V? What will we do? So basically what you need to do is take another current source which is Iref and use a device which is this is all this is M4 which is 1/4 of M1. In other words, if all these devices are W by L, this is 1/4 W by L. Okay. All right, and as we just discussed, the output resistance of this is what is called the high swing cascode. It's called the high swing cascode, and the like the regular cascode, it has very high output resistance, but the accuracy is poor because the drain source potentials of M2 and M1 are different. Okay. So the last thing to do is what would we ideally like to do? We'd like to have a current mirror where the output resistance is high, the accuracy is good, and the minimum voltage is, I mean, what can it, what is the smallest that we can have? If you want GMRO square, the minimum headroom that you need is 2 delta V. If you want GMRO square, you're stacking 2 devices, and the minimum voltage needed to keep each of those devices in saturation is delta V. So you cannot presumably get away with the minimum voltage which is smaller than 2 delta, right? So so basically what we need to do therefore is to make sure that the I mean, what we'd ideally like to do is to basically see if we can not only get the high output resistance of GMRO whole square, we also avoid this error in the output current by, which is fundamentally due to the different VDSs of M1 and M2.